Let us then continue on through our work with 1.3. So yesterday we had established what is a function, what is the domain, the range, all that fun stuff, and started our work into kind of taking a look at some properties of functions. How can we classify the behavior of some functions? We're going to get a much more kind of in-depth look as to what's going on with those momentarily here in 1.6, which we'll cover next week. But for now, we're going to look at a very specific type of property. Now, I will say, I want to preface this, this is going to feel a little bit disconnected from what we were doing yesterday. The book that we are currently working with, the Pearson book, puts a lot of emphasis on understanding functions through their graphs. I prefer to kind of approach it from understanding the function through the function itself. What is it saying? Kind of what is the mathematical sentence that we are working with? And then using the graph as kind of a supplemental tool to kind of build up a visualization of what we are describing. And so there are a couple of things that are a little bit different, a little bit out of place than how I would normally approach this. And to that end, in this particular section, there is a whole kind of subsection that focuses on like graphical symmetries and all that, and I'm entirely glossing over all of that because I don't want to. But also in part because I think that a lot of these properties that we're going to see are very robust for just looking at the equations themselves. So certainly there is some graphical connection here, but it's going to feel a little bit disjointed because my focus is going to be less on the symmetry, more on the equations themselves. So if it feels a little out of place, sorry about that. Let us suppose that we are dealing with some kind of polynomial function. We'll talk more about exactly what that means in Unit 2, but we'll just say for now it's going to be a collection of different powers of x. We'll say for our purposes, maybe we're looking at like negative 6x to the fifth minus 7x cubed plus 3x, where I do want to make a quick little note that this is like 3x to the first power, but we don't write to the first power just because it's kind of redundant, right? Raising something to the first power doesn't change that. Any kind of observations that we can make about this particular function? Any patterns that we see? Is that a hand raise happen? Yeah. Yeah, absolutely. We only have odd powers for each of our variables here. So notice here we have that to the fifth, we've got to the third, and then we have that invisible to the first, like we said before. So a polynomial, noticing here, we only have odd powered functions. Now I'm going to do something that again feels a little bit out of place if we were talking about transformations. This would be a reflection. We will look more specifically at that a little bit later. But what I'm going to do is I'm going to replace the x here with something very specific. I'm going to plug negative x into this particular equation. And I just want to see what is this going to do to my function when I plug in this negative x. So kind of good practice here using my parentheses, plugging in negative x for x. Oh, that's good practice. All right. And what do we notice about when we take each of these negative x's and raise them to an odd power? What's going to happen to each of them? We're going to end up with the negative version of each of these, and when we multiply that negative through, we're going to see this kind of change to our function here. So negative x raised to the fifth will be negative x to the fifth times negative 6 will give us a positive 6x to the fifth. Negative 7 times, in this case, negative x cubed is going to give us a positive 7x cubed, and then positive 3 times negative x, a negative 3x. x. What happened to our function? All the signs flip, right? The stuff that originally was positive, by stuff, I mean these coefficients, the coefficients that were originally positive have now all become negative, and the coefficients that were originally negative have now all become positive. It's almost as if we've multiplied everything by -1, or just kind of distributed a negative all the way through our function. In other words, we might say something along the lines of p of -x is the same as, is equal to, negative p of x. Plugging in that negative x essentially just flipped all of the signs for my equation. Right. There are several functions that are like this. I'll maybe more specifically say there are several parent functions that are like this, although exactly what a parent function is something that we will get into again in 1.6. And to that end, this is a fairly interesting property. You really don't see this all that often. We looked at a few functions, and we can kind of already go ahead and see that this is fairly remarkable. For instance, if we're looking at something like 3 to the power of x, we're certainly not going to see this property if I plug in this negative x here. In this case, f of negative x, giving us 3 to the negative x, which gives us 1 over 3 to the x. Remember, dividing by 3 x times. We see pretty quickly that this does not follow this property at all, right? In this case, plugging negative x in is nothing like multiplying by -1. It has instead its own bizarre, weird effects that seem completely disconnected. So it's a fairly unusual property, and it's also fairly useful to be able to classify functions that are all going to share this property. Taking inspiration from the fact that these functions are going to behave like a polynomial with odd exponents, we describe these particular functions as functions that are odd. So an odd function is going to be any function where if I plug in negative x for my function, it's almost as if I am multiplying by -1. I get the negative version of my function. With polynomials, we can see it very quickly. It's those odd powers, but we'll also see trig functions that display this. We could do the exact same thing. I'm going to tweak my function ever so slightly here. Let's look at an adjusted version of this polynomial, where I'm just going to drop the power of everything that we see here by 1. Right, so instead of -6x to the 5th, let's consider what's going to happen with -6x to the 4th. We'll look at -7x squared, and we'll look at plus 3. Technically 3x to the 0, but x to the 0, anything raised to the power of 0 is just what? Not 0. 1. Raising something to the power of 0 makes it 1, and so we can think that there's like an invisible x to the 0 here. Just remember that this is in fact an even-powered kind of term, but we will see that it might as well just. All right, what's going to happen here if I do the same thing? If I take this p prime of -x, what's going to happen when I plug in the negative in this case? It's not going to change anything, right? If I plug in -x here, -x to the 4th is just positive x to the 4th. Negative times negative times negative times negative is a positive number. -x squared is positive x squared. And so plugging in -x, I get the exact same function as if I was just plugging in normal x. Again, functions that describe or that exhibit this kind of behavior have a special name. Again, this special name linked to the fact that it shares this behavior with polynomials that have an even, that only have even kind of exponents here. An even function is going to be any function where if we plug in a negative, it's almost like we didn't do anything at all. F of negative x is the same thing as f. And what we have here, this definition for even and odd functions, is both a definition. This is how these functions are defined, what it means to be even and odd. It's also a nice little test for us. If I need you to figure out if a function is odd or even, a really easy way to do that is to just plug in negative x and see, does it look like a function that is even? Does it look like a function that is odd? Or does it look like something entirely different altogether? It's entirely possible for functions to be neither even nor odd, but we'll see examples of that as we go. Technically, you could confirm this by plugging in specific examples. So like you could plug in 1 and -1 to confirm this. I do want to caution you, though, it is better practice to plug in -x just because it's a little more precise. -x tells you whether this works generically. Plugging in 1 or -1, maybe you just got lucky and the two examples you picked happened to tell you that this was a. Is that a question, Dylan, or just okay? You're good. You can just. Any questions with our definition of an even function, definition of an odd function? All right, let's take a look at a couple examples here. I am looking page 6, looking at example 2. We are trying to figure out whether the function that is given is even, odd, or neither. All right, A and B are going to be a little bit quick. We get the terms even and odd from something very, very specific. And so looking at A, what would we think? Is this function going to be an even function or is it going to be an odd function? It's going to be an even function. Notice here we've got an even power, x to an even power, but that's not our technical check. Certainly if I asked you to justify why something was even, you could say it is a polynomial with only even exponents. I would give you full credit for that. But the technical check is we want to plug in -x. And what are we going to see in this case? Well, when we plug in -x, nothing changes. Therefore, our function is even. Fantastic. What about with B? Plug in -x or looking at the exponents here, what kind of prediction would we make for B? Is this going to be even, odd, or neither? This is going to be odd, right? We've got x to the first power, we've got x cubed. This should be odd, and lo and behold, you plug in -x, and that is exactly what you get. Okay. C is interesting. We could multiply together, and I do want to clarify, the f of x that this is referring to is from example A, the g of x is from example B. So I'm not just saying take two random functions that we've never seen these ones defined here, multiply them together. We could do out that multiplication. We could go through and multiply. Let's see if we can't figure this out, though, just using our definitions of what it means to be even, what it means to be odd. So how do we check to see if h is going to be even or odd? What's my test? Plug in what? Plugging in -x, absolutely. So in this case, we say, well, what is h of -x? Substituting in -x into this side of the equation, we get that this is going to be f of negative x times g of negative x. What do I know about my function f here? What kind of function is it? It's an even function. So what is f of negative x the same as? If I plug in the negative, I get just f of x. Fantastic. So this is the same thing as just f of x. All right, because this function is even. Yes, sure. That was from example 1. So this f of x here, this f of x here are the same f of x. We said that this one is going to be even, and then the next one will be odd. All right. What about g of negative x? What kind of function is g? It's an odd function, and so when I plug in the negative, what should I get for g of negative x? Negative g of x, fantastic, times negative g of x. I'm going to do some reordering here, bring that negative all the way out to the front, and I get that this is going to look like negative f of x times g of x. So when I plug in negative x into h of x, what does it look like? Does it behave like an even function, or does it behave like an odd function? It behaves like an odd function. I plug in negative x, and it's the same thing as if I multiplied by negative 1. And so, absolutely correct, this function would be odd. And you get the same thing if you had taken, distributed, looked at that. You get a bunch of odd exponents, and that's true. But this is actually a really powerful result. We kept things very, very generic. This could have been any even function and any odd function. So what kind of conclusion can we draw? Well, if you multiply an even function and an odd function together, you will always get an odd function. It's kind of like multiplying a positive and a negative number. So for instance, if I were to multiply two odd functions, what kind of function would I expect to get? So two odd functions multiplied together, you'd expect to get an even function because it's like a negative times a negative, which would give you a positive. All right, one more here. This one's a little bit deceptive intentionally. Try to keep you guys on your toes at least a little bit. X minus 2 all squared. When we look at the graphs, it's going to be, or when we talk about transformations, what this minus 2 does and why it disrupts the symmetry that is intrinsic in what we are looking at here with these even and odd functions. That's going to become a lot more clear. But what does this look like just at first glance? It looks even, right? We've got this squared up here. Certainly it's trying to pass as even. But actually, when we plug in negative x, it's very unclear to see how we simplify it. More than that, if we were to try to plug in concrete values, like 1 and negative 1, we'd get something very interesting. If I plug 1 into this function, I get negative 1 squared, which is 1. If I plug negative 1 into this function, I get negative 3 squared, which is 9. It's not behaving like our even function or our odd function. Why is that? Well, if we simplify this ever so slightly, you'd have to do your Punnett square, multiply x minus 2 times x minus 2. When you do that, we see that actually this function is x squared minus 4x minus 4. It has parts that have even exponents. It has parts that have odd exponents. And so this function behaves like neither. As far as like symmetry arguments go, I'm going to commandeer this. Functions that are even are functions that are the same when you are positive and negative. These are functions like x squared. And functions that are odd are going to be ones where if you were to kind of flip it by 180 degrees, you would get kind of a mirror image. These are going to be functions like x cubed. Things like that. And so we do certainly see that there is something to be said here about the symmetry of these functions. And so part of the reason why something like x minus 2 squared is not an even function is because that breaks that symmetry and where it is centered. It would instead look something like this. It shifts it over in some direction, and that ruins the symmetry. Or it doesn't ruin the symmetry, it just means it's not symmetrically centered around 0 anymore, it's symmetrically centered around 2 instead. So if you were to plug in 1 and 3, you would get the same result. If you were to plug in 0 and 4, you would get the same result, but it's no longer centered around 0. So it's no longer an even function. All right, questions about evens and odds, or specifically even functions, odd functions? Yeah. So say again? So think of multiplying an even and an even like multiplying a positive number and a positive number. So positive times positive is going to be positive, so it's going to be an even function. Perfect. Yeah. If I were to give you two functions multiplied together, two functions divided, and I were to ask you to justify whether one was an even function or an odd function, you definitely can make an argument from here on out. I'm giving you permission, like saying that an even times an even is always even, or an even times an odd is always odd. You can also plug in negative x and see what you get. The safest bet to do is if I ask you whether a function is even or odd, plug in negative x and see what you get. That's just universally going to be the same. Any other questions? Good question. All right. One final thing to look at. I don't want to dwell too long on this. It is something that is worth seeing. Certainly, if you are taking the CLEP test, it is something to at least be familiar with. But I really don't want to focus too hard on it. That is going to be piecewise functions. Part of why I want to talk about this is because they look a lot scarier than they actually are. So a piecewise function here is going to be a function that has different definitions over different intervals. So maybe this is a function that acts like it's x squared when our numbers are negative, but acts like it's cosine of x when the numbers are positive. Or maybe this is a function that likes to pretend to be 12 when we are between -1 and 1, but is acting like the x cubed function everywhere else. All right, these are functions that just are kind of broken apart into different pieces, and so we just kind of treat each piece separately for our definition of the function. Okay. So looking at, again, page 6, I think the best way to approach this is to look at an example. In this case, we are given a function where if our value of x that we are looking at is less than -1, our function is going to behave like x cubed. If our value of x that we are plugging in is between -1 and 4, then our function is going to behave like the constant number -2. And if our value of x gets large enough, in this case surpasses 4, then our function pretends to be the square root. The way you deal with this is fairly simple. whenever you're looking at a particular value of x, you just look at what definition, what interval you fall in, and you ignore everything else. So for instance, let's say I wanted to know what f of 0 is for this particular function. Which definition am I going to use here? Am I going to use my top definition of x cubed, my middle definition of -2, my bottom definition of the square root of x? I'm going to use this middle definition here because 0 is between -1 and 4. So we go to that middle definition. What is the output there? Well, normally we would plug 0 in, but in this case, is there anything to replace? No, it's kind of like that example we looked at with 1.2, and so this is just going to be that constant value, that -2. Normally you would plug 0 in. There's just nowhere for it to be plugged in. All right. What about something like f of -3? Where's this going to live? Which definition is this going to fit? It's going to fit our first definition. So we treat our function like it is a cube function. We cube -3. This will give us -27. One last one. What's going on at f of 16? What is this going to behave like? Going to behave like that third option. In this case, it is like our square root function. And so plugging that into x, we get 4 for this particular value. So you just identify where am I living, which interval do I fall under, and you ignore everything else. It doesn't matter what this top line says when we're between -1 and 4. You disregard it. Doesn't matter what that bottom line says when we are down by -20. Just these functions are ones where you want to be particularly paying attention to the endpoints. Notice in this case how I don't have any or equal to signs here. So if I were to ask you what f of -1 is, none of these would work as the definition for f of -1 because -1 is not less than -1, and it is also not greater than -1. And so -1, just with how I defined this function, is not part of this domain. That would fit that third rule that is situationally defined domains. I left -1 out here. I also left 4 out here. But you would want to pay attention, for instance, if I were to have put the line here and ask you what is f of -1, which equation do we use? We use the one where it is the or equal to. In this case, there is no or equal to, there is no f of -1. Okay, graphing these. What is graphing these going to look like? Mostly, it is just identifying those kind of places where we're trading off functions, those places where we switch from one definition to another, and then graphing how it looks to the left of that transition and to the right of that transition. So for instance, looking at our first 2 lines, where do we first see a trade-off from one definition of my function to another definition of my function? At -1 is where we are going to have our first trade-off. Now, what is our top function doing, or what would it like to be doing at -1? Essentially, if I were allowed to plug -1 into that top equation, what would I get? I'd get -1. I would get the point -1, -1. That is the terminating point for the first piece of our definition. Now, is it part of our graph? Is -1 an input that works for that particular piece of our graph? No. How do I represent wanting to get really close to that point without actually touching that point? What do I use? Normally, so if this were interval notation, I would use a parentheses. For the point on the graph, what do I use? I use that open circle. I use that open dot. fantastic. So at -1, we've got this open dot, and we say to the left of this, we're acting like a cube function. So something like this. Ish, I don't know. All right, what else is going on at -1? Well, we're handing off to that middle function where we're just -2 all the way through. Normally, you would plug -1 in here. Notice in this case that it doesn't change anything. We're that constant function -2. And so we are also going to see this open dot here at -2, and we run with that all the way till 4. All right. Then we see our second trade-off at 4. Again, perfectly happy, constant function, that's fantastic. But then where does our other function pick up? What is the point that it really wants to be when x is 4? What is that output going to look like? If I were allowed to plug 4 in, what is the output that I would get? 2. Now, is the point 4, 2, is that going to be a part of my graph? No, because I don't have that or equal to sign, but I'm certainly going to try my best to approach it. And so we're looking at a function that is the square root function, but kind of picking up from that point 4. Okay, from this, what do I care most about in terms of what you know? I care a lot more about your ability to, say, evaluate a piecewise function at a particular value than I do your ability to accurately graph it. All right. This first bit of what we were doing, plugging in the various bits, identifying which pieces of the domain does this match to, correctly plugging it in, evaluating what that's going to be. This is the more important part of the piecewise stuff. But I wanted you to have seen the graphing bit as well. So focus on, again, this kind of like equation representation. And just kind of keep in mind that the graphing is not as scary as it would seem. Questions from 1.3? How are you feeling? Okay, good. Better than the evens odds or better than the domains ranges? Domains ranges. Okay, that's fair. They're tricky. They're tricky. I will be the first to admit that for sure. Okay. So from the survey, the two big things that people wanted to go over from what we've kind of gone over before: domain range practice, hence the bell work. But then also a lot of people were asking about number 108 from section 1.2. In terms of what you would maybe expect on quiz, 108 was just kind of like an extension problem from that section. It is not going to be the kind of problem that I would ask on a quiz. The notes are a very, very good representation of what you could expect on the test. Are a very, very notes and bell work. And in a bell work, if I give you like a hint, wink, wink, nudge, nudge, it's going to be but yeah, so 108, it's a good extension question. I think it is worth going over and kind of talking through in terms of like, how would I recommend approaching kind of a complex modeling question? How would I break it down if I were lost and confused on where to start? But by no means is it what you're going to see on like the quiz that you have on Thursday. but I do think it is worth going over. You are more than welcome to use this time to work on that 002 classwork, which is no longer due tonight, instead due tomorrow at 11:59, quiz on Thursday. But I do want to go over that number 108 since somebody last. So 108 deals with a chemistry problem. The idea is we are mixing two different concentrations of sodium iodine and trying to figure out, if we mix this amount of sodium iodine with this amount, what is the concentration going to be of the resulting mixture. For these kinds of problems, if you are lost, if you're not sure where to kind of work, where to start, I always recommend start by defining what your variables represent. I think it's very, very easy to kind of just jump straight into a problem and just get very, very lost very quickly. And a nice way to ground yourself is just like, what does this stuff represent? What are the objects kind of at play? And then maybe what am I missing? What are the other pieces of information? How can I use that? So of interest in particular for number 108, I'm curious, how do we define, according to the problem, X? And how do we define the output S of X? So what does X represent? And then what does S of X represent? Yeah, passive solution. This is 1.2. Yeah, this is the very last problem on 1.2. Right there in that last sentence, what does it say our X represents? What does it say our output is supposed to represent? Fantastic. So our X here is millimeters of the 10% solution. Right? And then what is the output telling us? It says like the amount of sodium iodine. I like to think of that as like the concentration. Or we can think of the amount of NaI. A couple of things that are missing here, though, from this. There are a couple of pieces of information that we haven't used. For instance, one thing that we haven't used is the fact that we don't just have a 10% mixture of sodium iodine. What else do we have? What's the other kind of thing? What are we mixing it with? We're mixing it with a 60%. So there's some other, I'm going to use this like little placeholder variable. It's going to disappear very quickly. I'm going to call it X hat, which maybe this is just like the amount of 60% sodium iodine. All right. And then there's one final piece of information that kind of gives us the relationship between the amount of sodium iodine, 10%, and the amount of 60%. For instance, if I were to use, let's say, 10 millimeters of the 10%, how much of the 60% do I have to use? It's like one final little. What does my total solution kind of volume need to add up to? Yeah, so it needs to be a 50 millimeter solution. In other words, when I take my 10% and I add it with my 60%, I should end up with 50 millimeters worth of solution. This problem actually lends itself very nicely to systems of equations. Unfortunately, you're being asked about a single variable equation that we were trying to model. So let's eliminate one of these parameters. Let's get rid of one of these variables. The way we're going to do that is we're going to take our second variable, in this case, the amount of 60%. We're going to write it in terms of x. Subtracting x from both sides, we get that the amount of 60% is just 50 minus however much 10% we use, right? If I use 10 millimeters worth of the 10%, then I should have 40 left over for the 60%. Okay. And so now we know that our concentration here is going to be however much the 10% contributes. Well, it's going to contribute 10% of its volume. So 0.1 or 1/10 times our x plus however much the 60% contributes. This is going to be 60% of its volume. What is its volume? Well, that's 50 minus however much x that we are using. Or as a system of equations, this would be like x plus x hat equals 50, and then s is equal to 0.1 x plus 0.6 x hat. And you would use the substitution or elimination method in order to solve it. But as a single variable equation written like this, no parameter, or no extra parameter. And then you're just doing the substituting in 30, interpreting your answer. That's going to be like some concentration when you have 30 milliliters of blah, 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 blah. Right? So an interesting modeling problem for sure. Again, the way I approach these modeling problems is just like a really quick routine first step is what does my stuff represent? Like, what are the variables that I'm using? What am I looking for in terms of an outcome? And then is there any leftover information and how can I use that? How can I kind of incorporate that into the framework? Again, good little modeling challenge problem, not something that I would expect you to be able to kind of produce on like this, but certainly worth talking about. All right. One other problem that I want to kind of draw your attention to, this is less to do with the math involved. There is a math question in here, more to do with the fact that this information currently is stuck forever in my head, and I want you to also share that fate. You'll notice that there was one question, it was 131, that I accidentally forgot to remove the sticky note from, so you can't really see it. And I just wanted us to kind of enjoy this question together. It has to do with number of animal deaths per year, and like which are the deadliest animals. So it talks about sharks may be scary, but they were only responsible for 3 deaths worldwide in 2014. The world's deadliest creatures, ranked by number of human deaths per year, are mosquitoes, snails, and snakes. The number of deaths by mosquitoes exceeds the number of deaths by snakes by 661,000, and the number of deaths by snails exceeds the number of deaths by snakes by 106,000 deaths per year. So snails are killing 106,000 more people per year than snakes are. I just wanted you all to have that information. There's a math question in there. It's like figure out how deadly snails are. But you know, you get that kind of rough estimate from just set up the problem. So may you live a little bit more in fear of snails, I guess is the takeaway from this class. All right. Any questions from the 0013 classwork that we would like to go over during this time? If not, you are welcome to use this as free time, or not free time, but working through your classwork. Yep.